Eulerian and Hamiltonian path and cycles. Okay, so let's get started here. Objectives. Okay, use the term of transversal, Eulerian, semi-Eulerian, Hamiltonian, and Hamiltonian cycle. Identify transversal graphs, which we'll do in a couple of different ways. Identify Eulerian and Hamiltonian travel in practical examples as well. Okay, so transversal graphs. As a bit of a reminder, transversal means that you can pass over all of the edges without lifting your pen. Okay, you want to go over every edge, all right, and you can repeat the vertices but not the edges. Okay, so we'll see lots of examples of this one. This all relates to Eulerian and semi-Eulerian. So when we look at this example here, is that we've got our starting point. We could in fact cover over all of this in the following way, all right, and we can see that every edge was in fact coloured. But we started up at A and we finished down at C, which is perfectly fine. All right. So as we continue through this, right, not all graphs are transversable. So for example, the second one down here, when we have a go at this one, right, we get stuck at this point here where we can't actually cover this edge here and we can't cover this edge here, which makes it not transversable. All right. Whereas that first one, which we saw, was transversable. All right. Identifying transversable graphs. So there is a couple of ways that you could in fact do it. Right. There is obviously by hand, testing it to see whether it works. However, it's not very efficient and we need to come up with a better / more systematic way to do this. It all has to do with the degree of the vertices, and as a reminder, that has to do with whether they are in fact odd or even. Okay. Now, we're going to look at this a few times. So, is it transversable? Are all the vertices of even degree? If they are, it's transversable. Are there exactly two odd vertices and the rest are even? If so, it's transversable. If not, it is not transversable. Okay, so we're going to follow through this flow chart a little bit. All right, as I just suggested, these are the two possibilities for whether it be transversable here. Exactly two odd and the rest even, or all even vertices. Okay, if we have more than two odd vertices, it's not going to be transversable. All right, so let's have a look at two examples we started off with. Right, writing the degree of each of the vertices here is it would have 3, 3, and 2. So looking at the first one is that we could see, well, it's going to be transversable because it has exactly two odd vertices. Here's an odd vertice, here's an odd vertice. Looking at the second one, every single one of these is an odd vertice, right, making it not transversable. Okay. As we look at each of these, we could look at 2, 2, 2, 2 for the degree of the first one, which follows through this first link up here, which means yes, it is in fact going to be transversable because all of the vertices are even. When we look at our second one, right, what we can see is that we're going to have, oh, sorry, we'll just finish that. That's how it would in fact represent. Okay, all of the vertices in terms of their degree, we see we have an odd one and an odd one. Two odd, making it transversable as well. When we look at our third one, we'll see the arrows in the diagram. Here we go. Yep, check that, and we've done it. Over on the third one is we see we have 3 odd or 4 odd vertices, should I say, meaning that it is not in fact transversable. Now this all relates to this Eulerian and semi-Eulerian. Okay. Right, firstly, it must in fact be connected, and we're going to relate it back to these 3 graphs we just saw before. Everything we've done is already looked at this. Okay. So if something is Eulerian, is that it is in fact a closed trail, which means that you're going to start and finish at the same point. All right. So for it to be Eulerian and start and finish at the same point, is that all the vertices must have an even degree, like that first example did, and we'll see that in a second. You can start and finish at any vertex, and that means you will finish at the same vertex. So this was a nice example of a Eulerian trail where we started in the top left, and it wouldn't matter where we started as we go around, is that we started and finished at the same. And what we noticed that the degree of every single one was degree 2, making all of them even. So in summary, we would say is, well, if all 4 are even, or all of the vertices in this case are even, what it means is it means that you will have an Eulerian trail, meaning you start and finish at the same point. Semi-Eulerian, okay, as you may have suggested, it suggests it's an open trail. All right, same things, right? Open or visit every edge once and only once. All right, and what it's going to mean is, in relation to what we've just spoken about, is it's going to have exactly 2 odd vertices. We saw this with our second example here, where we had 2 odd vertices. So in this example here is that we started here and we finished down here. These were my 2 odd vertices. So here I had a degree of 3, and down here I had a degree of 3. So when we see this happen, is that I'm always going to start and finish at the odd vertices. If I did this in the other order, and I started down the bottom, is I would in fact finish at the other one. Right, and we would call this semi-Eulerian. So semi-Eulerian is an open trail, effectively. Okay, so now updating this flowchart is that if it is all even, we would have a transversal / Eulerian. If we have exactly 2 odd ones, is it would have a semi-Eulerian. If it's neither of these, it's not transversal. Okay, let's keep going. Second part of this is Hamiltonian path. Okay, Hamiltonian path involves visiting all the vertices, but not necessarily all of the edges. There's not really a systematic way of doing this. All right, it's kind of a bit of guess and check. Okay, so within this, all right, this diagram here is we visited all of the towns, but we haven't crossed over this road or this road. It doesn't matter. Okay. A cycle, start and finish at the same vertex. As we can see here, once again, we haven't passed over this edge, or this edge, but we have in fact finished and passed over all of the vertices. You do notice we start and finish the same, making it a cycle. So a cycle means you start and finish at the same vertex. Okay. Hamiltonian graphs start and finish at the same, right? Said to be semi-Hamiltonian if it is open, so that means that you start and finish at different vertices. However, you've passed over all of the vertices. There's no rules, trial and error for this one. Right, the applications is places, towns, all right, might be delivering before returning back to the depot, which would indicate a cycle. Okay, they're kind of the pretty common questions that you would see with in relationship to this. And obviously we're going to have weightings and stuff like that come into this a little bit later, when we start to talk about shortest path and stuff. Here are some places. Okay, so let's answer some questions here first. Going back to our semi-Eulerian and Eulerian. Why is this semi-Eulerian but not Eulerian? Well, remember, looking at the degree of all of them, is that we have 2 odd, making it semi-Eulerian. Write a semi-Eulerian trail that begins at Tulungai. That works with us because that is one of the odd vertices. So here is our path, as you can see, starting to highlight now. Okay, passing over all of the edges. Write a Hamiltonian cycle that begins at Healesville. Keep it nice and simple for yourself for part C. If you're starting at Healesville and there's a path around the outside, just take the path around the outside like so. Okay, and don't forget within this, I'm missing it just here, it should be back to H as well. Okay, that's it. Give the questions a go. Thank you.